Hello, this is a walkthrough for the Fall 2017 Exam 1 for Calc 3. Okay, question 1. We are told that there are 3 points which lie within a unique plane P, and we are told that the line through 0, 0, 0 and 1, 2, is normal to P. So let's draw all of the information we need out. So we have this plane, and let's say our origin is right here, and then we have the vector 1, 1, 1 sitting there. We also know that the normal vector to the plane, that's kind of hard to draw, but hopefully this gets the point across. The normal vector to the plane will be at a 90-degree angle to this 1, 1, 1 vector, and we know that this guy can be expressed, well, it does go through the origin, so I'll make that a little more clear, as going from 0, 0, 0 to 1, 2, and since we know that this guy, 1, 1, 1, lies within the plane, and 1, 2, is our normal vector, we will have a 90-degree angle here. And all we need to do for this question, it's surprisingly simple, is see that the dot product of these will have to be 0. So 1, 2, dot 1, 1, 1 has to be equal to 0. So this means that 3 plus a is 0, or a is -3. So a particle has an acceleration given by that a of t expression there, and some initial velocities and positions, and we're told to find r of 1. So it doesn't matter that this is a vector valued function. We can just treat every component individually, and we should come up with our correct answer. So we know that in order to get from our acceleration expression to our velocity expression, we need to integrate every component of a of t and then adjust things to match our initial velocity. So the integral of a of t dt is going to be, let's see, 1 over 1 plus t, 2/3 t to the 3/2, and 2t. And each of these components really has a plus c in it that I'm not putting down, because it's kind of a waste of time, because all we're going to do now is take a look at our initial velocities, which are 1, 1, 1, and we'll make sure that when we plug in t is equal to 0, that everything matches up. So when we plug t is equal to 0 into the x component, we do get 1. So we don't need to add anything in there. But for our second component here, we are going to need to add 1, so that when we plug in 0 for t, we get our initial velocity of 1, and then the same goes for our final component over there. And now all we need to do is integrate v of t dt, and we will get ln t plus 1. Let's see, 4/15 t to the 5/2 plus t, and t squared plus t. And all we have to do now is make sure that this works out for r of 0 equals 0. And you'll notice that it looks like they're giving us a scalar here. They like to do this, especially in the final. They will sometimes use this notation where if they capitalize a scalar like that, that means it's that capitalization means that they're really trying to express a vector. So this is just the vector 0, 0, 0, and that will come up later with surface integration and Stokes' theorem, which is a whole nother thing. So let's make sure r of 0 is 0. So for our x component, if we plug in 0, ln of 1 is going to be 0, so we're good there. We're also good for our y component and our z component, so we don't need to add anything. All we need to do is plug in r of 1, and we'll have our answer. So this will give us ln 2, let's see, 4 over 15 plus 15 over 15 is 19 over 15. And here we will get 2. And there is our answer choice B. Okay, so question 3 asks us to find the principal unit normal vector of the space curve R of t. So our principal unit normal vector, n of t, is equal to the derivative of the unit tangent vector of t over the magnitude of the derivative of the unit tangent vector of t. And this unit tangent vector of t is just r prime of t over magnitude. Oh, god damn it. Where this unit tangent vector of t is just r prime of t over magnitude r prime of t. Okay, so let's figure all of this out. R prime of t is going to be negative sine t plus cosine t, negative sine t minus cosine t, and 1. Okay, and then the magnitude of this guy, well, we're going to need to do a bunch of multiplication. Our magnitude is going to be the square root of sine squared t minus 2 sine t cosine t plus cosine squared t plus sine squared t plus 2 sine t cosine t plus cosine squared t plus 1. Okay, and this looks like this is going to work out to root 3, because this guy's going to cancel with this guy, then we're left with 1 pair of sine and cosine, 2 pairs of sine and cosine, and a 1. So that's root 3. And so our unit tangent vector of t is going to be 1 over root 3 times negative sine t plus cosine t, comma, negative sine t minus cosine t, 1. Okay, we're halfway there. So now we know that we need our derivative of our unit tangent vector. And it's important to realize something at this point, because we're going to be essentially making a unit normal vector. What we found here, this 1 over root 3, does not matter. That's going to get canceled out in the end by finding our normal. So it does not matter what magnitude our unit tangent vector is. It doesn't have to be unit necessarily, and it'll make our lives easier if we just drop that right now. So this derivative is going to give us negative cosine t minus sine t, negative cosine t plus sine t, and 0. And we can work everything out and see. You can almost see by just looking at it, we're going to get a cosine squared t, a sine squared t, a plus 2 cosine t sine t, and then over here we're going to get the same cosine squareds and sine squareds, but we're going to get minus 2 sine t cosine t. So the magnitude of this entire thing, and you should probably check it for yourselves, is root 2, and so we're going to multiply by 1 over root 2. And thankfully, we see that answer choice C matches this exactly if you pull this negative sign out. So this question is a little bit of a little bit of a pain, but they have not asked something like this since, so got that going for us. Okay, let's consider these limits. As a general rule, if they give you 2 limits, one of them doesn't exist and the other one does exist in some sneaky way. And but don't take my word for it. Let's work this. Excuse me. Let's work this out. So number one, we're given the limit as x and y both approach 0 of all this stuff. So first, just plugging in 0, 0, we see that we're going to get 0 over 0, which is no good, but the limit could still exist. And what we'll need to do to prove that the limit does exist is see if we can factor anything out and cancel things to leave us with something nicer. And in this case, we can't. We can't factor out an x or a y because we have terms without terms that don't include x's and y's. So that's no good. And so at this point, it's probably worth it to try the two-path test just to prove that it doesn't exist for good. So really the only two paths that you ever need to check are x or y equals 0 and y equals x. So if x equals 0, this whole thing is going to be 0 over 0 plus 0 plus y squared, which when we apply our limit is still going to give us 0 over 0, which is no good. But if y is equal to x, we are going to get x squared over x squared plus x squared plus x squared. And that is going to evaluate down to 1 over 3. So because we applied the two-path test and we saw that given two different paths, the limit or our function approaches different values, therefore the overall limit in kind of 3D space cannot exist. So that brings us down to A and B. And if you couldn't figure out this one over here, you can just kind of apply the general trend of one existing and one not existing to find our correct answer, which is A. But I really hope you don't get stuck having to do that, because if we plug in 0, 0, which should always be your first step, always try to directly evaluate it. Don't just assume that it'll evaluate to 0 over 0. We will get 0 over e to the 0 plus e to the 0, which is 2. And so this is a real 0. This is not some kind of undefined nonsense. So A is our correct answer. This question is much easier than it looks like. It is. We've got all of these crazy curves happening here, and it's kind of scary because A and D are very, very similar. They're just looks like they're this one is a cosine wave. This one's the sine wave for A and D, and that's a little scary if we have to differentiate between those two. But it's actually incredibly easy because we see that z is a function of x and y, but it's only defined for x values. So it should be undefined for all y values. And what that means is that for any given x, for any given x value, it should have one corresponding z value, but it should also be defined for every single y value. And I'm kind of mixing saying defined and undefined. It should, and we can actually use the correct answer choice to kind of show this at this point, because we see if we were to look into 3D space a little bit, we would see, and this is not accurate, but we would see some z values. So this is like this would be a peak over here, and we have a trough over here. If you can kind of see that in 3D space, if we kind of look at it from an angle, but you can kind of see how every x value has exactly one z value up in the z space, but it's completely undefined on y. It can have any y value, and B is the only one that satisfies this. All these other ones are just kind of nonsense for our purposes. We are told that the function f of x and y has the following properties, and we are told to find the partial derivative of f with respect to s at s of t of 0 and 0. And importantly, we see that x and y are both composed of s and t. So whenever we have a function that whose input variables are composed of other variables, this is a case for the multivariable chain rule. And in our case, we're trying to find fs, which is going to be fx, fx xs plus fy ys. And that's just our general equation for our multivariable chain rule. And this is pretty much one of the easiest ones that you will run across. Because not only is it only in 2D, sometimes they give it to us with a third dimension where we would have to do fz, zs added on here, but they also give us these partial derivatives of f with respect to x. But take a look, they're giving us two sets. We're given a set for x and y are equal to 1 and 1, and a set for x and y equal to 0 and 0. So we're going to have to figure out which one to use. Well, we know that x is equal to e to the s minus t e to the t, whereas y is equal to e to the t minus s e to the s, where s equals 0 and t, that's a terrible t, where t equals 0. So let's plug these in and see what values of x and y we are dealing with. So x is going to give us 1, and y is also going to give us 1. So we're actually dealing with the points x equals 1, y equals 1. And so we can disregard these 0, 0s that they give us. And this is something that they often like to do, giving you kind of fake values, fake inputs that match your kind of secondary variable inputs, and that can easily trip you up if you don't recognize it. So now we know that this fx in here is going to be a 3, and this fy is going to be a 7. All we need to do is find xs and ys. So xs is going to be e to the s, and ys is going to be negative s e to the s minus e to the s. And at 0, 0, this will give us negative 1, and this guy will give us 1. And so we can plug these in. Oh, that's not a 3, that's a 1. And ys is a negative 1, and we get our answer of negative 4. Just make sure. Yes, okay, we're good. The length and width of a rectangle are measured as 10 centimeters and 4 centimeters respectively, with an error in measurement of at most 0.1 centimeters each. And we're told to use differentials to estimate the maximum error in the calculated area of the rectangle. So there are two ways you can do this question. You can either recognize that as side length increases linearly, area increases exponentially, and what pretty much what that means is that we're going to get the maximum change in error if we go from, let's kind of draw this out. If we go from 10 by 4 to 10.1 by 4.1, that's going to give us a bigger change in area than if we go down to 9.9 and 3.9. And then all you have to do is recognize that our area here is going to be 40. Our area here, if you multiply things out, is going to be 41.4. And it doesn't matter what this area is because we know that the difference from here to here is going to be less than our difference from here to here. And so we have our answer here, which is 1.4 centimeters squared. But instead, we can actually do this the way that they want us to. Let's see if I still remember how. Using differentials, because we know that our area of the rectangle is going to be length times width, and we can say that our partial derivative of a with respect to L is W, and our partial derivative of a with respect to W is L. And okay, it's all coming back to me. This is a couple months after I've done since I've tried a differentials problem, and this kind of apparently disappears from my mind faster than these other questions, because a lot of the time you can just do this and cheat your way out of it, but sometimes they give you values that are a little annoying to deal with, and you've got to actually do the math. So we can say that the total error in measurement is equal to AL times delta L plus AW times delta W, where where delta L and delta W are just the potential errors in the measurement, which in this case for both is going to be 0.1. And then we know that our AL is W and our AW is L, and we can also replace these because we know that our length is 10 and our width is, well, I just mixed things up, but it's okay, is 4. And we see that this will just work out to our total error in area being 1.4, and we just confirmed what we saw earlier. Let's find the point xy at which f has a local minimum. So this is going to be a second derivative test question, and we know that with the second derivative test, like we do every time, we are going to have a matrix in the end to deal with, which is going to be made up of fxy, fyx, and fyy, and then we have some rules for this matrix. If the discriminant is greater than 0, then we have two options. If fxx is greater than 0, we're dealing with a min. If fxx is less than 0, we're dealing with a max. If the discriminant is less than 0, we're dealing with a saddle point. And if the discriminant is equal to 0, we don't know anything. And so we are looking for a local minimum. So we are trying to find points that satisfy both of these requirements here. But in order to go down that road, we have to take a bunch of partial derivatives. We need fx and fy just to get going here. This is going to be 2x plus 4y minus 2. This is going to be y squared plus 4x minus 13. And all we're looking for is are the points that make both of these guys 0. So let's try to figure that out. It's a little bit of a pain, but we can say that 0 equals 2x plus 4y minus 2, and 0 equals y squared plus 4x minus 13. Well, let's see, we can replace our 4x in here with our x's that we have up here. We can take this guy and say that 2x is equal to 2 minus 4y, or 4x is equal to 4 minus 8y, and we can go stick this in here, where we see that 0 is equal to y squared plus 4 minus 8y minus 13. This will simplify to minus 9, and we can factor this into, oh yeah, minus y minus 9, y plus 1. Okay, so we see that our potential y values for a local minimum are y equals 9 and -1. Okay, so we know that if y is equal to 9, it has to satisfy this guy right here. And actually, I'm gonna clear things up a little bit so I have a little bit more space to deal with. We can even get rid of all this. There we go. So let's see. We can find our x values pretty easily here, because if y is equal to 9, then 0 equals 2x plus 36 minus 2, or, let's see, this will be 34. So x is equal to negative 17. X equals negative 17. And if y is equal to negative 1, we will get x equals 3. So after all that, we're like halfway done with our question. We know that our two ordered pairs that can possibly be minimums or maximums or saddle points are negative 17, 9 and and 3, negative 1. And this is great because we see that these are two potential answers that they're already giving us. So we've probably done something right, or at least we're on the right track. And so now all we have to do is set up our final matrix, which is going to be made up of fxx, which will just be 2, fxy, which is 4, fyx, which is 4, and fyy, which is 2y. Okay, and we said that we're looking for the conditions where the discriminant is greater than 0 and where fxx is greater than 0. Well, fxx is always going to be greater than 0, so all we're looking for is the value for y, which makes this discriminant greater than 0. And we see that in order for that to be true, that 2 times 2y minus 16 has to be greater than 0, which we can also say that 4y has to be greater than 16, or y has to be greater than 4. And the only case where that's true is when y is equal to 9 up here. And that is our answer. Okay, the depth of the lake at a point is given by that function of x and y. Assume that x and y are measured in miles. If we have a boat at the point 2 miles, 1 miles, and it's sailing in the direction of the vector 3, 1, what's the rate of change of the water depth? So these questions are kind of hard to identify sometimes as to what they want you to do, but this is a directional derivative question because we're looking for the rate of change of some measurement, in this case it's water depth, in the direction of some vector. And those are the two kind of conditions that we're looking for whenever we're trying to identify if something's a directional derivative question or not. So we know that for our directional derivative, we're going to need an fx and an fy. This is going to be 6xy. And over here we'll get 3x squared plus 10y. And we know that we're going to be dotting this. We can form our gradient vector from this. So 6xy, 3x squared plus 10y. We know that we're going to be dotting our gradient vector with the unit vector of the direction that we're pointing in. And so this is going to be 3, 1. The magnitude of 3, 1 is root 10. So all of this times 1 over root 10. But we still have some variables kicking around in here that we can remove because we know that we are sitting right now at the point 2, 1. So right over here we're going to get 12, and here we'll get 12 plus 10, so 22. And now all we have to do is take this dot product, which will give us 36 plus 22, so 58 over root 10. And there's our answer. Okay, question 10. We're looking for partial z, partial x at 1, 2, 1, where z is implicitly defined as a function of x and y, by this whole thing right here. So first off, let's put this in a form where it's all on one side. We're going to have the tangent of pi xyz minus x squared plus z squared is equal to 0. And then we can take this whole thing and apply the equation that we like to use for this implicit differentiation thing, where in this case we are going to be looking for d dx divided by d dz, and that will give us partial z partial x, which is what we're looking for. So d dx is going to give us secant squared pi xyz times pi yz minus 2x, and d dz will give us secant squared pi x yz times pi x y plus 2z. And we can evaluate these because we know the values for x, y, and z. In both of these cases, we're going to get secant of 2 pi, which is just 1. So we can get rid of all of that. I'm going to move things back over a little bit, where pi yz is going to be 2 pi, 2x is going to be 2, pi xy is going to give us 2 pi, and 2z is also going to give us 2. So we are going to get 2 minus 2 pi over 2 pi plus 2. In other words, 1 minus pi over pi plus 1, which is answer choice D. Let's find the tangent plane to this surface at this point here. So our equation for this, because it's explicitly, it's implicitly defined. It's not explicitly defined, is going to be fx, x minus x naught, plus fy, y minus y naught, plus fz, z minus z naught is equal to 0. And so all we have to do is find these three partial derivatives and plug everything in. So fx, fy, and fz. Well, fx is just going to be y squared z cubed, which at 3, 2, 1 is going to give us 4. Fy is going to be 2xy z cubed, which will give us 6, 12. There we go. And finally, fz is going to give us 3x y squared z squared, which will be 4 times 12, which is 36. And before we do anything, we're actually going to simplify all these down, because we can divide everything by 4. We will get 1, 3, and 9. So we can plug things in now. Fx is just 1, where x naught is, remember, it's just going to be our x value of the point that we're evaluating it at. That's just going to be 3. Fy is 3, where y naught is 2. And fz is 9, where z naught is 1. So now, if we've done everything correctly, this should be equivalent to one of our answer choices over here. And in fact, we see that there's only one choice where we get 3, 6, 9 as our coefficients. So that one better be correct. And let's see, 9. Yeah, it is, because we will get x plus 3y plus 9z minus 3 minus 6 minus 9, which is the equivalent of 18 on that side. Let me just make sure. Yep, we are good. And finally, sometimes they like to throw very odd questions in as the last question on these exams. especially on the final, but here's one. In this case, all we're looking for is the derivative of f at 1, where f is the dot product of two vector valued functions. Or, well, really it's not the dot product, it's multiplied together. And all you have to do is recognize that we can apply the chain rule on these guys. So f prime of t is going to be, and by chain and by chain rule. Sorry, my calc one is getting mixed up. By chain rule, I mean the product rule. So because we're multiplying these two together, and we're only dealing with one variable. So this is going to be equal to u prime of t times v of t plus u of t times v prime of t. There we go. And let's see, we know that u prime of 1 is 1, 2, 3. So 1, 2, 3. And we know that v of t is t comma t squared comma t cubed, but t is equal to 1, so this is just going to be 1, 1, 1. And then we're adding u of t, where u of t is given right here as 1, 1, 1. And then we want v prime of t. Well, v prime of t is just going to be 1, 2t, 3t squared, otherwise known as just 1, 2, 3. So the anticlimactic ending to this super weird question is just doing these two dot products, where we're going to get 6 plus 6. And that's our answer. Okay, this one was a little bit of a struggle for me. It's been 4 months since I've touched this exam. Hopefully that was helpful for you.